Hello and welcome to Lecture 1 on the topic of electric charge and force. This is the beginning of a lot of topics in electricity and eventually electricity and magnetism. So let's start. We have to start somewhere. Okay, so we're going to talk about insulators, conductors, and Coulomb's law of electric forces. Okay, it's an important equation. Our objectives are to conceptualize the idea of electrical charge and how charge can move in materials that are insulators and conductors, relate Newton's laws to the electrical force as defined by Coulomb's law, so you have some named laws here, establish some common constants in electricity and magnetism, and understand the units of those constants. Okay? All right, so let's look at our key terms. So the first couple terms, insulator and conductor, are terms that you've probably seen before in everyday parlance. Well, what are they? Well, an insulator is a material that impedes the movement of charge. Okay, we'll talk about what charge is in just a minute. But in other words, charge, whatever the heck that is, doesn't flow very well through insulators. Okay, for example, wood and rubber. Okay, if you need to protect yourself from an electrical wire, you need an insulator. Okay, ceramic is another good insulator. A conductor, on the other hand, is a material that promotes the movement of charge. I bet you can guess what the examples are going to be. Water is pretty good, but the best by far are metals. Okay, so metal wires, any piece of metal is a good conductor. Okay, now it turns out that if you're a good conductor of charge, you are also a good conductor of heat. Those things go hand in hand. Okay, all right. So what is charge? We probably have some idea from everyday experiences, but let's give the physics definition of what is charge. It is an intrinsic property of particles, okay? And by particles, we're talking about the proton, the electron, and the neutron here, okay? Now, things can get a little bit more fundamental, but we won't cover them in this class. So for us, we can think of these as the building blocks of matter and the possessors of intrinsic charge. Intrinsic charge, that is, okay? Now, I point out here that unlike mass, charge can be positive or negative. But why would I talk about mass all of a sudden? Well, the reason is because up to this point in your physics curriculum, you've only ever seen one other intrinsic property of, well, particles, and that was mass. That was it. This is a new player. This is new fundamental physics. Okay, there are not many intrinsic properties of particles, and charge and mass are by far the most important. Okay, but there are some key differences between mass and charge despite their similarities. The biggest, the elephant in the room, so to speak, is that charge can be positive, like a proton, okay, or it can be negative, like an electron. That's really different because there is no such thing as positive and negative mass, obviously. It is measured in the unit of the Coulomb. Okay, that's the unit of charge, just like the unit of mass is the kilogram, right? And the dimensions of the Coulomb. And we deal with so many different constants, so many different variables in this semester of physics that it's very important to keep grounded with some of the building block ideas of all these different values. And that's dimensions, which break everything down into mass, length, time, but we also need something else. And that is I. And what does I represent? Not intensity, that's what you're thinking, because we've seen I for intensity. Well, with that matter, we've seen I for moment of inertia, but neither here nor there. What I is the electric current. Now, are we talking about electric current today? Are we talking about electric current in this lecture? No, that's a future chapter. But the reason I mention it is because it's considered the base unit of all electricity and magnetism, which is pretty amazing. Everything from magnets to generators to just electric fields all has one base unit, which is represented by the dimension I for current. I for current, okay? Now, you might wonder, why is charge not the base unit? It just isn't, okay? We'll talk about the units of current, which are the ampere, later when we need to. But the dimensions then of charge is time to the first power multiplied by current to the first power. And conceptually, current is just charge over time, because it's the flow of charge, how much charge flows past a certain point in a certain amount of time, right? So like meters per second, but in this case, it's charge per second. And meters per second, of course, would be velocity, okay? And velocity is a flow, so is current a flow, okay? But to get back to the base unit of charge, this is an intrinsic property of matter, it's the Coulomb, all right? Now, really what we're doing here, since I mentioned current, I have to at least clear the air before we move on, is in this lecture and in this chapter, we're talking about something called electrostatics because everything's at rest. Now we might have something move in that we'll find an initial acceleration, but we're not actually equipped to deal with moving systems. We will deal with moving systems that involve both electricity and magnetism and the interaction of the two in later chapters. Okay, so now let's talk about a way that we can build up sitting charge, resting static charge, in two processes known as conduction and induction. Okay? So conduction is the movement of charge through direct physical contact. Okay? A momentary current. We're more interested in the final product. So here we have a negatively charged rod. Okay? It has a bunch of negative particles, maybe electrons, right? Likely electrons. Then we have a neutral sphere. Okay? It doesn't have an excess of electrons or protons. Maybe it has an equal balance of the two. Okay? Because it probably isn't just devoid of anything, right? There's probably some particles that compose the sphere. So neutral really means equal amounts, right? Rather than nothing. Then we're going to bring the negative charged rod into contact with the neutral sphere. And the result is a slightly negatively charged sphere and rod. Okay? Okay? And that's because the electrons are going to distribute themselves as far apart away from each other as possible. More on that in just a moment. But then if we separate our rod, we are then left with a slightly negatively charged each sphere and rod. See? Now they're both negatively charged. See how that worked out? Okay. So that's conduction. That's conduction, direct contact. But what is induction? Well, this is the movement of charge through action at a distance. Okay? Now, action at a distance, if it looks familiar, that's great, because it's the term that's been used for gravity, because gravity is this strange force that just permeates space. You don't have to touch something to experience its gravitational pull. You are pulled on by Earth even if you're not sitting on the surface of Earth. So that idea of action at a distance also applies to electricity, to electrostatics. Okay? So if we have a negatively charged rod and a neutral sphere, just like we started with conduction, and we bring the negatively charged rod close to our neutral sphere, but not touching, just close, it will pull all the positive charges to it. Because, and I haven't said this yet, but you may know it from the everyday science facts, opposites attract as far as charge is concerned. Negative charges like electrons attract positive charges. Okay? Now, in reality, if this is a metal sphere, there actually aren't any positive charges that are free to move. They're tied up in the nuclei of the atoms that make up our sphere. However, there are electrons that are free to move as long as it's a, you guessed it, conductor. Well, those electrons will get pushed away. So effectively, there's a building up of positive charge because all the electrons have been evacuated from that side of the sphere. They've been pushed to the opposite side. Okay? Through induction, action at a distance. Then, if we connect the sphere to ground, well, those electrons will just get pushed further away because they're being pushed after all. They're being accelerated, they're experiencing a force, and as long as there's no like friction to slow them down or very little, they'll just gradually get pushed further and further away. Okay, so then if you disconnect this ground wire, you can think of this just as a wire connected to some large metal object or literally stuck in the ground. Well, what's happened now is those electrons are gone. So now if we then pull our rod back to some distance further away, then we've got a negatively charged rod and a positively charged sphere. So induction is interesting like that. It can result in two opposite charges rather than two equal charges. Okay, now polarization is kind of like this picture right here, with all the negative charge on one side and the positive charge on the other. And it is the concentration of negative and positive charge on opposite sides of an object or atom. That's what we call as polarized. So polarized is opposites on either end, just like the poles of a planet. Okay? Here's a picture of a polarized setup, like a dumbbell with a positive charge over here and a negative charge over there. They could be different magnitudes of charge, right? Measured in the coulombs, or they could be the same. But the point is that it's a polarized situation. Okay? All right. And this object itself is called a dipole. All right. And we'll work with an example of that in the next lecture. The dipole is the name for this type of arrangement with positive charge on one end and negative on the other. Di for two, pole for polarized. Now, finally, Coulomb's law, the thing we're really going to be working with and solving problems with, and that I've hinted at some key ideas of already. So Coulomb's law is a law that defines electrostatic force. Forces at rest. Well, charges at rest, experiencing a force. Excuse me for saying forces at rest. I meant to say charges at rest. The law says that the force between charged particles is inversely proportional to the square of distance between the particles. Where have we seen it inversely proportional before? Think about that. Where have you in a physics class seen inversely proportional before? Gravity, okay? Gravitational force is also inversely proportional to the distance between the two masses that are gravitationally attracted to each other. Okay, so same idea here. Coulomb's law, just like the universal law of gravitation, is an inverse square law. That's the kind of jargony way that physicists refer to these things, okay? But remember that key difference? Coulomb's law says that the force is repellent between like charges, like a proton-proton or an electron-electron, and attractive between opposite charges, all right? And that little extra fact about charge, the fact it can be both attractive or repulsive, is so important for making electricity both more complex and more useful than gravity. And there's also the big fact that the electrostatic force is way, way stronger than the gravitational force, which adds to its utility. Okay. All right, here are key formulas, which is a bit of a misnomer here on the title. Now, in other lectures, it's very well suited because mostly these are just a long list of constants. But there's one formula, and that is Coulomb's force law right here, okay? And so it says that the force F is equal to whatever K sub E is, multiplied by Q1 times Q2, which are charge 1 and charge 2, measured in, you guessed it, coulombs, represented by the uppercase C, divided by R squared. Well, R squared has got to be, well, R, in other words, has got to be the distance between the charges, because we're squaring it. It's inversely proportional to the square of the distance, right? Okay, but what is that Q sub E thing? That's called the electrostatic constant, okay? It is a constant of the universe that is derived from the speed of light, okay? But we're not getting there yet. We will. We in fact will, okay? But for now, we just need to know it's a constant of the universe. And interestingly, it's equal to 1 over 4 pi times epsilon naught. This is the Greek letter epsilon, subscript 0, pronounced as naught. So I would say epsilon naught. And by the way, this 4 pi epsilon naught is all in the denominator, even though it's not clearly shown with the parentheses, kind of a shorthand way of showing it. Okay, and that epsilon naught is itself called a constant. It's called the permittivity constant. But you see that we don't really need to bring up the permittivity constant, not in this lecture at least, because the electrostatic constant is just a constant times permittivity, right? Because pi itself is a constant, 4 is just a number, right? And so, so as is 1 for that matter, it's a ratio. So, really, it's if we know one constant, we know the other, okay? And so we're only going to be using the electrostatic constant, but epsilon naught, the permittivity constant, will become more important as we move on to other ideas, okay? All right, and then we've got a bunch of constants of just common things that come up since we're talking about basic physics here, okay? So one is going to be the charge of an electron, okay? So an electron is negatively charged, and it has a charge of negative 1.6 times 10 to the negative 19 coulombs. So it's a very small amount of charge, because times 10 to the negative 19, that's like a millionth of a trillionth, okay? Very, very small number, very small amount of charge per electron. Now the charge of the proton is exactly equal in magnitude, but it's positive instead of negative, okay? But the magnitudes are identical. And this amount of charge, 1.6 times 10 to the negative 19, is called the fundamental charge. It turns out that there's actually something called a quark that has 1/3 of that, but the name stuck. So we call it the fundamental charge, okay? Now, a neutron has no charge, okay? So you won't see it come up in many of these problems because it wouldn't be affected by the electrostatic force, in other words, the Coulomb force. It's not going to be affected by electric fields, which we'll talk about in the next lecture. So, neutrons are great, but they're not going to show up in these problems involving forces and the results of those forces. But here are a couple other things, because sometimes we're going to have an electrostatic force that's going to result in a motion, okay? And I pointed out that it really would result in an initial motion, an acceleration. But in order to solve for that, we need Newton's second law, F equals ma, right? Because if you want to find A, and you know F because of Coulomb's law, you still need m in order to find the acceleration, okay? Which means we need to know how massive these particles are. Well, it just so happens that they've been determined through careful experimentation. What are the masses of a proton, an electron, and a neutron, okay? Well, an electron has a mass of 9.11 times 10 to the negative 31 kilograms, right? One of the smallest measured masses out there. There's not many particles with less mass than an electron that are well known. Really, it's kind of the limit of our knowledge, okay? Now, a proton, you can see, is quite a bit more massive. The mass of a proton is 1.6726 times 10 to the negative 27 kilograms. But since this is a smaller number as a negative exponent, that means the mass of the proton is bigger. It's much bigger, okay? And the neutron has a mass that often is rounded to be the same as the proton, but we can see if we go down here to the decimal place, the third and fourth decimal place, that actually the neutron and the proton do not have the same mass. The mass of the neutron is slightly more massive than the proton, okay? All right, so let's finally get into some example problems that I want to show you so you can see what it looks like to solve quantitative problems involving these ideas and Coulomb's law. Now, I've broken these problems up into types, and I do this with all of my lectures. We have type 1, simple problems that involve Coulomb's force and Newton's laws of motion applied to a point charge in one dimension, so they're 1D problems. And then we have fairly complex problems that involve Coulomb's force and Newton's laws of motion applied to a point charge in 2 dimensions. So we went from simple to fairly complex, because adding another dimension does definitely complicate things. We have to consider, well, right-angle trigonometry, okay? All right, type 3, problems that involve Coulomb's force and centripetal force, okay? Centripetal force means circular motion, right? When you see that, just think circular motion. Type 4, problems that involve Coulomb's law, Newton's laws of motion, and a law of gravity. Oh, okay, well, I said there's sort of similar laws. It makes sense to put them together. Applied to point charges or charged objects approximated as point charges, okay? All right, and we're going to see one of those, and we'll talk about how, I will mention when we get there, how it's an idea that we'll definitely delve into in greater context later on. Well, let's get to it. Example 1, the force of attraction that a negative 40 microcoulomb point charge exerts on a positive 108 microcoulomb point charge has a magnitude of 4 newtons. There's our problem statement, okay? Now, one thing you want to pay attention to is this subscript right here, okay? No, not subscript, but this prefix, all right? Mu, all right? So it's the letter mu, Greek letter again, and it represents a millionth. And a millionth means 10 to the negative 6. So I could rewrite this as 40 times 10 to the negative 6 coulombs, okay? So it's 40 millionths of a coulomb. That's a microcoulomb. We're going to see a lot more of these prefixes than you would have in your first semester of physics. It's just necessary when we deal with some of these topics. So I want us to get used to us using them as soon as possible, okay? Well, the way to start this is to start with Coulomb's law, okay? So I just wrote it out, Coulomb's law. Straightforward, and I'm only going to be interested in the magnitude of the charge. So I'm going to take the absolute values of my 2 charges, ignoring the fact that one is negative and one is positive, because that will give me the magnitude. In other words, the absolute value of the force, right? So it's not telling me if it's an attractive force or a repulsive force. I can figure that out after I'm done, okay? All right, so then I just do some algebra here, and I'm going to go ahead and solve for r. You can see I had to take the square root to isolate r, and plug in all my values that are specific to this problem. And notice we got the 10 to the negative 6 because of the mu, all right? And then we had 2 of them, which is why it's squared. Here are the 2 values of the charges themselves, the absolute values. There's that 4 newtons, the force between them. And there it is. There is the distance, 3.12 meters. Now, let me ask you, would this be an attractive force or a repulsive force? Think of it, okay? Attractive, because they're opposite charge, okay? So there'd be 3.12 meters apart that experience a 4 Newton force that wants to pull them together. Okay, so in part B, if the 108 microcoulomb charge has a mass of 4.56 milligrams, then how long will it take the point charge to travel 1 meter from rest? Okay, so they started off, 3.112 meters apart. They're going to get pulled together, and one of them is going to get pulled 1 meter, okay, 1 meter. And how fast is it going to be going after it's been pulled 1 meter? Because it's speeding up the whole time. It's accelerating. Okay, all right, so let's figure it out, okay? So we're going to find the acceleration of the mass, which I'm gonna call Q, okay? Big Q, uppercase Q, just because it's going to be the one that has more charge, right? Makes sense, use the uppercase Q for the big one, lowercase q for the little one, like so, all right? Okay, and then we're going to go ahead and find the acceleration, okay? And then there it is, there's our initial acceleration. And then we'll have it go that distance, okay? So we have our 1/2 at squared, and then we'll find the time, okay? Now there's a big thing that we did here, okay? There's a big approximation, and I meant to actually add this to the wording of the problem, is we're going to approximate the time, which I should have said, find an approximation of the time by assuming that the acceleration remains constant. Because the acceleration won't remain constant because the distance is changing, okay, because it started at 3.12, but after 1 meter, the distance between them would be, well, 2.12. And at 2.12, if we plug that back into the Coulomb force, we would get a different force, which means we would get a different acceleration. So the acceleration is gradually increasing, okay? Now, the thing is that that's great. We need calculus to find it. This is not that difficult of a problem, but it definitely requires calculus to actually set that up and solve for the non-constant acceleration. So here, we'll just treat it as a constant acceleration with the caveat of it being an approximation, okay? All right. Now, what's definitely a fair value that doesn't require any approximation is this right here, the initial acceleration, because that is precisely the initial acceleration when their distance is 3.12, okay? And we could, for that matter, find the final acceleration and find out how much it actually changed by plugging in 2.12, finding the force, and then solving for the acceleration, and then seeing, was it reasonable to say that it remained constant? Probably a little questionable. Okay, all right, let's do our next example, all right? So two tiny particles having charge of positive 5 microcoulombs and positive 7 microcoulombs are placed along the x-axis. The positive 5 microcoulomb particle is at the origin. In other words, is at the 0 point on the x-axis. And the other particle is at the 100 centimeter or 1 meter mark. Where on the x-axis must a third charged particle be placed so that it does not experience any net electrostatic force due to the other two? Okay? All right. So, in other words, we need to find the balance point. Because if we think about the force, right? If we think of a third particle, it's going to experience opposite forces from the two charges. So I point out here that I'm going to assume that the third charge is positive, but we get the same result if the third charge was negative. So here, this is positive Q, and that means that it's being repelled. This is the force that's repelling it from the 7. And then this over here, this force, is the repulsive force from the 5 microcoulomb charge. See? So it's being repelled in one direction from one and being repelled in the opposite direction from the other. If we replaced it with a negative charge, well, then it just would be attracted to the 7 and attracted to the 5. Okay, but there's still always going to be opposing charges, which will allow us to find a balance point between the two. In fact, whenever you have two equal sign as in positive or negative, two equal sign charges, there's always a point between them where there's going to be a balance point, an equilibrium. That's the term, an equilibrium in force. Okay, where you could put another particle and it would remain at rest. Does that make sense? Okay. All right, so we want F net equals 0. This is very much a Newton's second law. Set up the sum of force equation, in this case in one axis, and then, well, solve for the value, okay? So here's the equation, all right? This is just Coulomb's law, all right? So we have a known charge and an unknown charge, Q, okay? And then a known charge and an unknown charge on the other term. Notice that one of them is positive, okay? That's this one here, and the other is negative because of just the definitions of being repulsed by the like charge, right? Okay, does that all make sense? And then it's equal to 0. And then what is x? Well, x is this value right here. Okay, that's what we're trying to solve for. And since the total distance between them is 1 meter, that means that this value is 1 minus x. So those are our two distances, x and 1 minus x. And we're squaring both of them because Coulomb's law tells us to. And this, of course, is the electrostatic constant, okay? Now we can cancel out the q, which means it's totally independent of what charge, any charge could be balanced, okay? And we can also cancel out the electrostatic force, okay? Or well, the electrostatic constant, K sub E, right? Because it's equal to 0. We just divide every side. 0 divided by 9.89 times 10 to the negative, or 10 to the positive 9, Newton meters squared over Coulomb squared. That's the constant, by the way. Well, 0 divided by that is just 0 after all. Okay, so then we just set this up and then solve for x, right? That's all I'm doing here. Right, and when you solve for x, notice you'd have to distribute the 5. I also canceled out the mu because the mu cancels out on both sides. There should be a cancellation there too. And so if you were to distribute this 5 in, well, what's going to happen is then you're going to end up with a quadratic equation, and you can solve it, graphically or using the quadratic formula, right? And that's where you actually get this value of 45.8 centimeters. Okay, hopefully that looks good. Make sure you can solve that problem. All right, question 1. How many electrons does it take to equal the mass of a proton? So when I have questions, these represent more conceptual, less quantitative. Although we are finding a number here, we're not using one of the typical problem-solving techniques. The reason I'm actually asking about this is I want us to have an idea of how much more massive the proton is, precisely. Okay? Well, here we're just going to find the number, n, for number of electrons, okay? And that's just going to be the mass of the proton divided by the mass of the electron, take the ratio of their masses, and we find out that you would need 1,836 electrons to equal the mass of a single proton. So the proton is indeed much more massive than the electron, okay? Even though they have the same charge. What is the percent difference between the mass of the electron and the difference between the mass of a proton and a neutron? Okay, so what am I asking there? Well, remember how I said the neutron is slightly more massive? All right, so let's find that difference. So delta M is just the difference between them, the slightly more massive neutron minus the mass of the proton. And we have 2.3 times 10 to the negative 30 kilograms. Notice this is pretty close to the mass of an electron, because the mass of the electron was on the order of 10 to the negative 31. So they're kind of close to each other. All right, there's a reason for that. There's a fundamental physics reason for that. But let's find out how close they are. Well, if we look at the percent difference, we'd find the delta M minus the mass of the electron divided by the mass of the electron times 100 to get a percent. And that gives us a percent value of 152%, which tells us that the mass difference is almost twice as massive as an electron. So you think of the neutron as, in many cases, being rounded to being the same mass of a proton. Okay, chemists do that a lot. But in fact, it definitely is heavier. In fact, it's 2 electrons heavier, or 1.5 electrons heavier. That can definitely matter in certain systems. Okay. All right, now let's go back to our common problem-solving types in this section, in this lecture. Okay, example 3. Consider a container of 2 grams of hydrogen. Okay, hydrogen, by the way, in its normal state comes as H2. All right, that's diatomic hydrogen. And 2 grams turns out is exactly 1 mole. Okay, and you've seen moles before in your physics classes. If you've taken a chemistry class, you've seen them. If you need to review moles, please do so. Suppose you removed all the electrons and moved them to the other side of the Earth. Now, the Earth's radius is 6,380 kilometers. We're going to need its diameter, which is just radius times 2. All right, and then here I point out n sub a is 6.002 or 6.022 times 10 to the 23 molecules per mole. Well, what is that number? Yep, Avogadro's number. Okay, so how much charge is left behind after you remove the electrons? Okay, let's see. So the idea is that I'd have Q, the left behind charge, is just going to be 2 times Avogadro's number times the charge of an electron. So 2 times that big number times the fundamental charge. All right, and so that gives me positive, because there's positive charge left behind if we took all the electrons to the other side of the planet, and it gives me a positive charge of about 19,000 coulombs. That's a lot of charge, but then again, there's a lot of atoms in a mole, okay? Okay, and then let's find the actual force, okay? So here we're gonna have the electrostatic constant, we're gonna have our 2 charges, because it's gonna be this charge on one side of the planet in a positive form, this same magnitude charge in a negative form as electrons on the other side of the planet. And there we have the radius of the Earth times 2 to represent the diameter, and we're squaring it because, of course, it's proportional to distance squared. Okay, all right, and here I've just plugged in the values themselves, and there we have about 2 million newtons. That is a lot of force. You know, and it really should kind of strike you that when we deal with electrostatics, huge forces are involved, because that also means that there would be a huge amount of work. Remember, work is force times distance in order to pull this off. Think about how much energy, because after all, work is related to energy, how much energy it would take to actually do this, to remove all those electrons and then move them that far away from the original atoms that they were next to. Because essentially you have to ionize them. That's the term of stripping electrons from an atom. So you have to ionize all this hydrogen and then through some large electric field, pull those electrons very far away, right? That could take a huge amount of energy. It would take about 2 million newtons times whatever the distance is to get the joules, right? So you can imagine that's going to be a lot of joules, okay? All right. Let's move on to the next one. Example 4, okay? So this is our first 2D problem. 3-point charges, 2 with a charge of 56.7 millicoulombs, notice this is milli, not micro, and a third with a charge of negative 33.4 micro, that one is micro, form an equilateral triangle with a side length of 45.8 centimeters. What is the net force, magnitude, and direction acting on the negative charge, the special one, the odd one out? Okay, so there it is, one in the corner. All right, and notice I've labeled them 0, 1, and 2, okay? All right, here's a little equilateral triangle. Zoom in so you can kind of see all the values, right? Equal sides, we'll call that R, okay? So what we need to do is consider the forces, okay? And we're going to consider them in terms of X and Y. So we're setting up a typical coordinate axis here. All right, positive x to the right, positive y up. Looks good, right? So we have a force of attraction pulling up to the side at a 60-degree angle. Why 60 degrees? Because it's equilateral triangle. And then we have a force of attraction pulling directly to the right. Okay? All right. So that's the setup. Now we need to split those forces into components if necessary, and then find the overall net force. All right? Because you know from vector addition that the overall net force is going to look like this, right? Because this is F1, because I can move vectors around, and then this would be F net. Okay? That's the overall net force we're going to solve for. All right, let's break this down. Okay, so first of all, here's the equation. It's a vector equation, which means we need to split it into components. Okay, this should look familiar to things you would have done with mechanics. Okay, some free body diagram. Okay, so here it is. Okay, notice that F2, that's this one here, doesn't have a y component, so I've just crossed it out. All right, and then I'm going to rewrite my net force equation in x, taking into account the appropriate component of this angled force, and not worrying about a component for the force being pulled towards 2, because that one is directly along the x-axis after all, okay? And then I factor out my like terms, so it looks like that, okay? And then I note here that Q1 equals Q2 equals Q, right? So they're equal charges. That's why I can kind of get away with just replacing them, okay? Oh, whoops. Okay, all right, and then we're just gonna carry on. So then we're going to get the y component. Now the y component is easier because after all, F2 doesn't have a y component. So the y component is just the y component of F1, as you can see here. Notice we went from cosine to sine, right? That's based on the angle, okay? Now we could have done this all in terms of 30 degrees as well, okay? But I didn't. So just all you need to remember is SOHCAHTOA, okay? SOHCAHTOA. All right. And then the net force, we're just gonna use the Pythagorean theorem as we would for any net force, okay? After all, it's a right triangle, all right? Plug in our values, plug in our numbers. All right, there it is. 1.41 times 10 to the 5 newtons. There, got it, okay? All right, looks good. All right, next example, example 5. A point charge of Q equals 2.5 coulombs. Wow, that's a big charge, by the way, right? Not micro, not milli, but just 2.5 coulombs. And a mass of 100 kilograms is stationary, and a second point charge of negative 1.3 coulombs and a mass of 30.5 grams is at a distance of 500 kilometers. All right, so wow, pretty far away, right? What velocity would the particle need in order to instantaneously achieve uniform circular motion at that distance, right? So let's see. Here's the setup. It's an orbit, okay? But it's an orbit that isn't driven by gravity, but instead is driven by electrostatics, okay? Now, in part B, I'm going to ask about gravity, and in part A, I'm going to include gravity, but we'll see what happens, okay? All right, because I'm going to stand by that it's driven by electrostatics. This is not a gravitational orbit. This is an electrostatic orbit. And you might be like, well, the thing that's orbiting is definitely not static, but the middle is, and the system isn't going anywhere, okay? Now, there are some important consequences. Since we do have a charge that is accelerating, there are some side effects of that, but we'll get to that in the future chapter. Okay? For now, we need not worry about it. In fact, all we need to worry about is a simple force balance, because we've got an attractive force between our oppositely signed charges, and we've got a gravitational attractive force as well. Okay? And those are going to equal what type of force? The centripetal force. Okay, so here is our sum of force equation in the radial direction. Rad here represents radial. Okay, so the radial direction. Fc plus Fg, because they're both pointing towards the center, so positive radial direction, are going to equal the centripetal force, which also points towards the center. After all, centripetal means center seeking. Right? And then I was just solve for B. All I've done is just cross multiplied and then taken the square root of both sides. Plug in all our numbers. There we go, there's a bunch of them. Okay. Right, I'll just put parentheses there. Okay, and there it is, 1,380 meters per second. Okay, wonderful. So, but then notice there's two terms. There is the centripetal force term, and then there's the gravitational force term. Now, since the gravitational constant is much, much smaller than the electrostatic constant, I drew just a small error. But like to scale, is the centripetal force about twice as strong as the gravitational force in this case? Let's find out, okay? Let's just do away with it. Let's throw out the gravitational force and see what number we get. Okay, and by the way, when I say that the gravitational constant is smaller than the electrostatic constant, look what I'm talking about here. Here's the electrostatic constant, 8.987 times 10 to the 9. So in other words, 8.987 billion, okay? And then over here, we got 6.67 times 10 to the negative 11. That's really different. This is 66 trillions. This is about 9 billion. That means that these numbers are 10 to the 9 plus 10 to the 11 apart. They're 20 orders of magnitude apart. Gravity is 20 orders of magnitude weaker than the electrostatic force, than the Coulomb force. Wow. Yeah, so they're pretty dramatically different, aren't they? That's when we say gravity is the weakest force. We do say that, by the way. Okay? All right, so if we ignore gravity, then our velocity from our sum of forces, since this force would be gone, simplifies to this. This would be the velocity with just electricity or just electrostatics. And we get 1380. Oh, I guess it rounded to the same number. What if we take the percent error? Okay, so I'm just going to take the velocity minus the velocity without gravity divided by the velocity including gravity. Okay? 0. Exactly 0. Yep, the 12 significant figures. But that makes sense. And this is, by the way, my calculator only includes up to 12 significant figures. That's because, remember, the difference was 20 orders of magnitude. So that means that gravity is completely inconsequential for such large charges. Completely can be ignored. Well, that's good. It saves us some work, right? Okay. All right. Well, let's look at an example where we can't exclude gravity, because there actually are some real-life examples where gravity and electrostatics can play together and where they both matter. But notice how we have to set this up. Let's look at this problem here. Okay, this is our final type of problem and our final page here nearing the end of this lecture. Example 6. A tiny 0.025 microgram spherical oil droplet contains 29 excess electrons. Oh, wow, 29 electrons. Well, remember, 1.6 times 10 to the negative 19 coulombs is the charge of a single electron. So if you have 29 of those, then you've got something on the order of like 10 to the negative 14, right? 10 to the negative 15, whatever, right? Right around there. So that's like a thousandth of a trillionth of a coulomb. That's a lot smaller than 1 coulomb. That's a lot smaller than even a microcoulomb, right? It's a millionth of a microcoulomb, okay? So it's even smaller than that, actually. So the point being that it's a very, very small amount of charge. And when you have that tiny amount of charge, then gravity and electrostatics can actually work together, but it requires tiny amounts of charge. And the reason I call it an oil droplet is because this is a real life experiment. It actually led to some of the first quantitative measurements of the fundamental charge in a famous experiment called the Millikan oil drop experiment. Okay, look it up. So the idea here is we've got this oil with its 29 excess electrons suspended between two stationary plates with opposite charges and separated by a gap of 12 centimeters. How much charge must each plate have in order to hold the oil drop steady? So we're going to treat these plates as particles. And this type of setup with two oppositely charged plates at some fixed distance, this is called a capacitor. Okay, specifically a parallel plate capacitor, but that's only the type we're going to talk about. And we will cover those in more depth in later chapters, okay? All right, but the idea is there's going to be an electrostatic force pointing one way and a gravitational force pointing the other way, and those two forces will balance out and the oil droplet will hover or levitate in the air, okay? Notice the positive y direction is defined as up. So we need to have the forces to balance to avoid motion. So F net y is just going to be the positive Coulomb force minus the negative gravitational force based on our coordinate system equal to 0 because there's no acceleration. This is a equilibrium situation, okay? And here we go. Here we have the electrostatic force, okay? Notice that there's two of them because there's both a, let's see, was it a positive? Okay, so there is an attraction to the upper plate and a repulsion from the lower plate. And that's why we end up with two terms to represent the total of the net Coulomb force. That makes sense? There has to be two terms, okay? Because of course, again, to say it again, the bottom plate repels, the upper plate attracts. Together, they make a net force. Then we've got gravity pointing down. Notice here I'm not using universal gravitation, I'm just using surface of Earth gravitation, so just m times g. Okay, depends on the situation, but here that would be the appropriate choice in this example. Okay, so then we just solve for q, right? Pretty simple because it's equal to 0. Notice that some of our, that we're going to be able to simplify everything, and our constants stick around though, okay? E, by the way, is the charge of an electron. That's the 1.6 times 10 to the negative 19. That's why there's 29 of them. Okay, h is the distance as shown in the figure. Okay, and when we plug in our values, we end up with 8.81 times 10 to the negative 5 coulombs. So the plates can have basically 88 microcoulombs of charge, which is a reasonable amount of charge because there's so little charge on the droplet itself. Okay, all right, cool. Actually, gravity and electrostatic forces working together in the rare case where there's very, very little charge. Okay, So, example 7, the force of attraction that a negative 40 microcoulomb point charge with a mass of 45.6 milligrams exerts on a 108 microcoulomb point charge with a mass of 1.22 grams has a magnitude 4 newtons. Oh, we've seen this before, right? How far apart are these two charges? Do not ignore gravitational force. Oh, okay, all right. So in this case, we'll go ahead and work this out, all right? So here's the setup here. The only difference here is I'm including the masses, okay? That's the only thing we're doing different from when we saw this before. So it's like the previous example, but including masses, okay? And here's the net force equation. Notice here that I'm using universal gravitation because it wouldn't make sense to use Earth's gravity because we're talking about the actual attraction between the particles, not the attraction to Earth, okay? And then we'll go ahead and solve for the length, okay? All right, and that's just plugging in the known value of net force, which is 4 newtons, and plug in all our numbers, and we get 3.33 meters. Okay, fine. That looks great. So how much role did gravity have to play? Do you have a guess? Okay. All right. So without gravity, we'll just exclude the second term, and we also get 3.33 meters. And then we look at the percent difference, and it's 0, just like it was with the orbital case. Because what does this problem have in common with the orbital case? Well, it's got charges on the order of microcoulombs. It's got a mass on the order of, well, in this case, milligrams, a very small mass. And that means that the force from electrostatics is much, much stronger. This would have had to been a tiny amount of charge to actually have a significant difference. Okay? Now I could rewrite the problem that way, and you might see it like that. But when it's not, when the values aren't as small as 29 individual electrons, then you better know what to expect, right? But you can always check the numbers, can't you? Okay, so this concludes our last example. Again, you can think about the kind of the categories they fall into, and you have practice problems that you can do as well. These are further practice problems color-coded into the same categories of 1D, 2D, and then problems that involve gravity and centripetal motion or circular motion as well. Okay, so you got a nice selection of problems, and these problems will also be included in the study guide. Okay, all right. Well, thank you so much for watching this first lecture on electricity and magnetism.